Okay, so if you're watching this, you've at least made it to my webpage, and this might be the first video that you're watching for my Math 142 class. So this is going to be a lecture for section 2.1. Almost guaranteed to put you asleep, so if you had coffee handy, it could hardly hurt. Before you get started watching the video, on my webpage, you'll see that I have some links to class notes, and not every time, but maybe 50% of the time, when I shoot a video, I print out the class notes and I use those class notes to give my, basically to give my lecture, and that's the case for section 2.1. So I printed out the link that said class notes for section 2.1. You'll definitely not want to print out every section of class notes if you're going through the class by watching the videos. You should probably turn the video on and see if I'm actually using my notes. If I'm using my notes, then you'll want to print them out. If I'm not using my notes, then you probably don't need to print them out. So you should have the class notes out in front of you. It also is probably going to help tremendously to have the book, and this is the book that I should have let you use for free, so shouldn't have had to purchase this book, but you want to have this Survey of Mathematics with Applications 7th edition book by Angel, Abbott, and Rundy, and you can get that for free from my office. And for this chapter, you don't need a special calculator, but at some point during the semester, you're going to want to have either a TI-83 or TI-84 calculator, and really these are a lot for chapter 11. You can't do chapter 11 without this calculator. A bit for chapter 12. There's some features that the TI-83 and 84 calculators have built into them that most calculators don't, that will help you. You'll appreciate it. And similarly, a little bit in chapter 13. So we're going to have probably about 6 days of the semester where you need to have one of these calculators. You don't need to go out and buy one of these. You can, if you want to, go to the bookstore. Go to the cashier's office at GCC North. Tell the cashier that you want to rent a calculator, and they'll rent you one of these calculators for $20 for the entire semester. And assuming that this is essentially your last math class, or your next math class is Math 156 or 157, where you don't probably really need a graphing calculator. If you don't already own one, and this is your lastest math class, I wouldn't buy one. I just go to the cashier and rent one. These get rented out fairly quickly, so if you wait a few weeks into the semester, you might go to the cashier and the cashier might not have one. You can't share calculators on tests, so that if you're sharing calculators during class, that's fine. But on a test, because it's too easy to pass answers, you can't share your calculator. So for this particular section, I'm going to use my class notes. In addition to my class notes, anytime I'm doing a lecture, there are homework problems that are be listed on the syllabus. And for this section, after you watch the lecture over section 2.1, you should be able to complete all of those problems. It might not be a bad idea as I'm going through the lecture to have the book open, and when you see me do a problem that's like a homework problem, maybe just get the homework problems done. So by the time you're done watching the video, you'll also be done with your homework. This is because as you're watching the video, you can hit the pause button, you can hit the rewind button, so you can pause me, do the homework problems, and just kind of be done with the whole section as the video finishes. So these problems will be easy to find in the book. Because they're all odd problems, somewhere in the back of the book there's going to be answers. So when I do a problem in section 2.1, if I'm not 100% confident that I'm correct, I can go into the back of the book on this appendix page, and I can check all of the answers just to make sure that I've done things correctly. In this section, as well as many of the sections in chapter 2, it's possible to have an answer that looks slightly different than the author's answer, that's still correct. So if you get an answer that looks a little bit different than the author's and you want to make sure it's correct, ask me and I'll tell you if it's an okay answer. Okay, so chapter 2 is a chapter on sets, and you may have never ever seen sets before, so this might be completely new to you. In intermediate algebra and beginning algebra, the topic of set builder notation is introduced, and we'll get a little more specific than we did in those courses. If you ever go for your master's, usually to get into a master's program, you have to take some test. That's a standardized test, either the GRE, which is the graduate. I don't even know what that means. But anyways, that's a test that the letters stand for something. And similarly, this is another test, graduate management admissions test. This is for like if you're going for an MBA. Anyways, if you're going to take a test to get into grad school because you want to get your master's, these tests that most students take before they get admitted to a grad school program have a math component, and a big chunk of the math component comes from this chapter 2. So this set theory is a big deal there. Other than in that world, a lot of the stuff you might not see again. Some of the stuff that we do a little bit later on, you'll actually, have maybe need to do it in your life. But this chapter is, I know for certain if you're going on to grad school that this material will at least pop onto those tests. So when you go to study for those tests, you'll want to have your notes from this chapter handy. All right, so I'm just going to start lecturing. Like I said, it's probably going to be painfully painful to watch these videos, but at least it's something. And as I go through the video, I'm going through my handout. From time to time, I'm probably going to open my book and say, now I'm going to do a problem in the book. So you want to have your book ready as well. When we get to the test over chapter 2, there will be a review, and there will never be anything on a test that isn't similar to a review question. By looking at this first page, I see definitions. I never ask definitions on a test. So the fact that I'm defining what a set is, it's nice. It's probably not going to help you solve problems knowing the definition of a set, nor is it going to be something that's going to be tested on, but I kind of feel obliged to put it in. So anyways, I have a definition of a set. A set is just a collection of objects, and the individual objects are called elements or members. So I defined a set as I defined set. It's not like the ultimate best definition, but it's a reasonable definition. It's just a collection of objects. So A is a set. Sets are usually named with capital letters. So I made A as a collection of 3 markers. So A is a collection of 3 objects. Each object is a marker, and each object we would call an element or a member of the set. So if A had these 3 markers in it, green, blue, and red, I can say the set A has the members or elements, the green marker, the blue marker, and as you'll find out, my writing is kind of crappy, so bear with me here. Hopefully I speak clear enough that you can figure out what I've written by what I said. So A is a set that has 3 elements. It has the green marker, the blue marker, and the red marker. If I didn't write the word marker after it and said A has the elements green, blue, and red, marker would be maybe implied. And when I list the elements, or I say the elements are members of a set, because elements and members are interchangeable words, the order that I speak the elements or I write the elements is not relevant. It doesn't make it a different set. So saying A is the set that has a green marker, a blue marker, and a red marker is no different than saying A is a set that has a red marker, a blue marker, and a green marker. Just because I spoke the words in a different order, that doesn't make it in a different set. So when I list the elements or speak the elements or members of a set, the order that I write them in isn't relevant. It's just the members themselves. So I made another example of a set. So a set's just a collection of objects. My set A had the objects were markers, and set B, the set is all the students enrolled in this class, so they're people. And again, I named a set with a capital letter. That's common in mathematics. If you're defining a collection of objects, which is a set, normally we give that collection of objects a name, and normally it's a name that has a capital letter. S might be a better name for the set, S meaning students. M might be a better name for the first set, M standing for markers. In the cases, the letters I picked, A and B, I just picked them because they're the first letters in the alphabet. And you can run across another set A that has completely different elements or members than my set A. So A isn't restricted for just this set. I can have 18 different sets, all call them A, just like there could be 12 different people with the name John. They're different people, but they all have the same name. Similarly, I could have 12 different sets that I call A. They could all have different elements in them. So that's the end of the first page, and we'll move on to the second page in my handout. And the second page starts to line up with the text a little bit, and I made some hints that we're going to be looking at some problems in the text possibly. So there's a set has to be well defined. Well defined means that any informed objective person can decide if a given element's in a set or not. And then I made a list of problems, and you have to decide whether the sets are well defined or not. Anytime I'm doing a problem, it would be great if you pause the video and try to do the problem ahead of me. If you need to watch me do a problem or two first and then pause and then do the rest of the problems by yourself, that would be fantastic. And then after you complete the problems, watch me complete them to see if I've done them right. Because I shoot most of these videos talking to myself in a room, there's a chance that I make a mistake. So if you do something or you see me do something that you think is wrong, just ask me, because there's a chance that it is wrong. So in each of the problems here that are supposed to help for problems 13 through 18 in section 2.1, I give a set, I give a name of a set, and I describe the elements that are in it, and then we'll have to decide if it's well defined or not. As I read through these, the first set A, the set of goofy dogs, that's not supposed to be well defined. Goofy is too objective of a word to determine. If I pick out a dog, not everybody might say that dog is goofy. So this is not a well defined set, because if I give you a dog, you may call the dog goofy when I don't. So it's not well defined, because not everybody that I'd ask if a dog is in the set or not would have the same members. Part 2, however, which refers to this question 2, what refers to the set B, that is a well-defined set. It wants me to find any student at GCC whose GPA is 3.0 or greater. It's got to be a computer report that I could generate, and if I pick out a student, I can tell you with absolute certainty whether that student belongs in the set B or not, because if that student has a GPA, then if its GPA is 3.0 or higher, the student would be in the set. So this set B that's defined in number 2 is a well-defined set. And then C, hopefully you've paused the video and you did C and D ahead of time. C, the set of good students, is not well defined, I guess, because good isn't an absolute word. I might consider somebody a good student and they might not consider themselves a good student. D, we're going to do almost no algebra in this class, but this is a well-defined set, because I can very specifically tell you, if you give me a number, whether it's in the set or not. If I tell you, is 3 in the set, you'd say, no, 3's not in the set because 3 squared is 9 and 9's not 16. If I said, is 4 in the set, you'd say, yes, 4's in the set because 4 squared is 16. So D, the numbers that are in D, not that it's relevant, are 4 and negative 4, because if you square 4, 4 times 4 is 16. If you square negative 4 times negative 4 is 16. I'm not asked to list the elements of D, or the members of D, but it is well defined because any number that you'd give me, I can tell you whether it's in the set D or not, because I could just square it and see if it's 16. So it's supposed to be the case that if we went to page 47 in the book, or 46 in the book, that you should be able to do problems 13 through 18. And if I look at the homework problems in 13 through 18, I have you do 13, 15, and 17. So this would be a wonderful time for you to do problems 13, 15, and 17. Those problems ask the same questions. It says determine whether each set is well defined or not. I'll do 14. 14 is the set of best internet websites. Best, if I give you a website, it's probably not going to be the case that everybody would say, yes, this is one of the best websites, this is or not. So 14, I'd say that that's not well defined, and maybe I'll abbreviate well defined with WD. And so you should be able to go through 13, 15, and 17, the problems that I asked you to do for homework, and quickly go through and decide whether the set is well defined or not. So that's the end of that page. I'll flip the page and get on to the next group, next page. And the next page talks about finite and infinite sets, and it introduces some new notation that is common with sets that I should probably talk about. So we have finite and infinite sets. Finite, it's possible, if given enough time and desire, to write down every element in the set. And an infinite set, you can't. It's not finite. It's impossible to write down every element. So I gave a set, and I didn't give it a name, but I put these brackets right here. And these brackets we call set braces. And even though I didn't name a set, I didn't say the set A is the set with the numbers 1, 2, 3, bop, 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 to whatever that is. Let me go backwards here. Believe it or not, that's 1 trillion. Our national debt's about 15 trillion right now. Anyways, so this is a set that I gave the elements of the set, and I have to decide if it's finite or not finite. And it's possible to write down every element. Notice I didn't write down every element, but I could continue to do this set. The next element would be 4, then 5, then 6, then 7. And I could go on for a long, long time, and eventually I can write down every element of this set. So this set is a finite set because given enough time, it's possible to write down every element. These periods here, we call those ellipses, and that just means you continue the pattern. Because the first numbers increment by 1, I'm assuming I'm going to increment by 1 all the way up to 1 trillion. So that's an example of a finite set, because it is possible to write down every element of the set. The next set, again, it's a set because it has these, I call them set brackets, or curly brackets, but set braces or brackets would be fine. And this is an infinite set because unlike the last set, there's no number after the dot, dot, dot. This just means that the numbers go on forever and ever. The last set, I'd get to 1 trillion and stop. But this set has 1 trillion and 1, 1 trillion and 2. It has, infinitely many numbers. The dot, dot, dot means the pattern goes on but doesn't end because there's no number to the right of the dot. So that's an infinite set. So the next 2 problems are supposed to help us with 19 through 24 in section 2.1. I have to decide if the sets are finite or infinite. And it's a little bit trickier because I didn't write the sets down with the elements and you have to kind of figure out what the elements are. And very specifically, 1 is supposed to be finite. If I started to write down the elements of the set, 3 is a multiple of 3, 6 is a multiple of 3, 9 is a multiple of 3. So those are all multiples of 3. 12 would be the next multiple of 3, then 15, 18, 21, and so forth. I'm going to use the nice notation. I'm going to go dot, 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 comma, and then the last number that's a multiple of 3 that's less than 100, because I teach math, I know that quickly in my head to be 99. This is an example of a finite set. I don't have to list all the elements. I just have to visualize whether I can, if it's possible to list all the elements or not. So that's an example of a finite set, because it would be possible to write down every number between 1 and 100 that's a multiple of 3. On the other hand, question 2, it's supposed to be infinite. And if I tried to start writing the fractions between 0 and 1, I could go like maybe 1/2, 1/3, 1/4, 1/5, and then dot, dot, dot. And that's not even all the fractions between 0 and 1, but that's already infinitely many fractions, because I can put 1 over any integer and get a fraction that is bigger than 0 but less than 1. So all of these are fractions between 0 and 1, and I could do that pattern forever. So this is an example of an infinite set. Again, I don't have to list the elements down like I did in these examples, but it can't hurt to. If this was a problem in the text, the author would just say this is finite, that's infinite, and be done. So now we're supposed to be able to do problems 19 through 24 in section 2.1. And if I look at the homework, between 19 and 24, I ask you to do 19, 21, and 23. So you should be able to go to the text, find the problems 19, 21, and 23, and figure out if they're finite or infinite sets. They should match up nicely with the problems that I did. I'll do problem 20 just so you can see me work a problem. So 20 says, is the set of multiples between multiples of 6 between 0 and 90 finite or infinite? And that's finite. It's like 6, 12, 18, 24, 30, 36, 42, and so forth. Between means it doesn't include the endpoint, so it's not going to include 0, 90 should I say, or nor 0, but that's not such a big deal. But for an answer to problem 20, I don't have to list down the elements that make up the set, but I know that I could list all the elements, and the fact that I could list all the elements would make that a finite set. The problem 21, a set of even numbers greater than 19. If I start thinking about the numbers, 20 is an even number greater than 19, 22 is an even number greater than 19, 24, 26, 28. There's no end to the list of even numbers that are greater than 19. So for an answer for 21, I should say that that's an infinite set, because it would be impossible to list all the even numbers greater than 19. So hopefully you paused the video and you got those homework problems done. And when you come back to the video, you see me finish up the rest of the page. And there are two special sets that this author uses a lot. The set of natural numbers, the author gives the letter n. And the set of natural numbers is an infinite set that starts at 1, kind of goes on forever. And then the empty set, which we write as a 0 or a 0 with a line through it, we usually give it the name phi. An empty set is a set with no elements. So those sets will come up semi-frequently in this chapter. The set of natural numbers comes up a bunch. The empty set comes up a little bit. So the empty set has no members or no elements. The natural numbers are any positive, bigger than 0 integers, numbers that don't have decimals or fractions. More notation. This symbol I read as is a member or is an element of. So this 5, that symbol means 5 is an element of A. And that means if I made a list of all the elements or members of A, 5 would be in that list. So here's my set, a new set A, not the set of markers that I used. I say that 5 is an element of A because when I listed all the elements of A, 5 is in it. So it would be correct to write 5 as an element of A. If I look at A, 6 is not in A. This symbol right here, this symbol, an element symbol with a slash, means is not an element. So this would be a true statement. To say 6 is not an element of A, that means 6 isn't in the list. If I made a list of all the elements of A, that 6 wouldn't be one of them. So for A, we can either something is an element or it's not an element. If it is an element, it's in the set. If it's not in an element, if it's not an element, it's not in the set. And you can, if you have the set listed out, then you can easily say if something is or isn't an element. This next page has some ways to describe or define a set. And not all of this comes in this section. I think some of this kind of laps over into section 2 too. But I threw it all in here. I could be wrong because I typed this up months ago and I'm lecturing without having previewed maybe far enough ahead. But I think there's something in here that isn't in 2.1 but is in 2.2. So there are at least 3 ways to define or describe a set. One is in words, and the way to describe a set in words is you have the most flexibility where we can use different words that mean the same set. So in this problem, I made an example. You probably should use a capital N for natural numbers. Let A be the set of natural numbers less than 3. That, for somebody, A is a well-defined set because a well-informed person should be able to describe the members or elements of A. Set builder notation. This is set builder notation. This, when I see this, the set braces with a vertical line in the set braces, when I see that, that's set builder notation. So these curly braces are the set braces. The letter before the vertical line in this problem is X. X is a variable, which means it can take on a variety of values. And next to the vertical line, I'm going to tell you the values that X could be. And this is tricky. When this right here, this means X is a natural number, which means X can only be the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. And then there's a comma. That comma can be replaced with the word and X is less than 3 but not equal to 3. That tells me the numbers that are specifically in the set A. The set A only contains natural numbers, and specifically it contains the natural numbers less than 3, and that's this, the numbers 1 and 2. So each one of these 3 are actually 4 descriptions of A all tell me that A has the elements 1 and 2. The easiest, probably the best way to write A in this case, because it only has 2 members, is just to say A is a set that contains 1, 2. And we call this way, if you physically list the elements or members of the set, we call that list form or roster form. Our author uses roster form more than anything. So words, this sentence right here tells me that A has the elements 1 and 2. And each one of these set builder notations also tells me that A has the elements 1 and 2, but the set builder form, if you're not used to reading mathematics, is cumbersome and tricky, and it isn't obvious that when I look at the set builder form that A really contains 1 and 2, but it does. And then the roster form is the probably nicest way to describe the set. It's the most efficient in this case. So the next group of problems are to prepare me for problems 25 through 34. So in a bit here, we're going to look at problems 27, 29, 31, 33 in the text. After I do these problems, you should be able to do those problems in the text. I'm asked to write a set in roster form and call the set B if no set is given or no name is given. So in problem 1, I'm given a set that's defined in words, and I'm supposed to figure out the elements of that set and write it in roster notation. Roster notation is just writing the set braces, and inside the set braces writing the elements of the set. Between doesn't include the endpoints, and natural numbers means it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So for this particular set, B is going to have the numbers 6, 7, 8, and 9. It's not going to have 5 and 10 because between doesn't include the endpoints. And it's not going to have a number like 11 or 4 because those aren't between 5 and 10, and it only has natural numbers. And had I said this, B is the set 9, 8, 7, 6, that would have been equivalently correct, because when I'm writing a set in roster form, the order that I write the elements in doesn't matter, just the elements themselves matter. So 2 gives me a word description, doesn't give me a name, so I'm going to call it B. I'm asked to write in roster form, so I write an equal sign, and then I set up my set braces, and then in the set braces, I want to write all the even natural numbers greater than 4. Greater doesn't include that number, so natural numbers greater than 4 are 5, 6, 7, 8, 9, and 10, but I only want even numbers. 6 is the first even natural number bigger than 4. 8 is the next one. 9 isn't. 5 and 7 aren't even. They're natural numbers, but they're not even, so they don't belong in the set. 10 belongs in the set. 12 belongs in the set. This is an infinite set, so it's impossible to list the entire set. When we have an infinite set, 3 is the kind of the minimum number of elements you need to show, and then we can put our dots in, our ellipses in. So B has the number 6, 8, 10, 12, ... And hopefully you can understand what elements are in B by looking at this roster definition. 3 is one of the rare times that we're going to do algebra. 3 says K is the set of answers to the equation 2 times K plus 1 equal to 6. To figure out what elements belong in the set B, I need to find any K that's an answer to that equation. So I'm going to go ahead and solve that equation. That equation is 2 times K plus 1 equal to 6. I'm going to solve this by clearing the parentheses. I'm going to multiply 2 times K and get 2K. I'm going to multiply 2 times positive 1 and get positive 2. So that gives me 2K plus 2 equal to 6. I'm going to minus 2 from both sides. When I do that, that gives me 2K equals to 4. And then I'll divide both sides by 2. On the left side, when I divide by 2, the 2's cancel, I'm left with the K. On the right side, 4 divided by 2 is 2. The only number that's going to go into the roster form of the set is the number 2, because 2 is the only number that's a solution to that equation. So the answer for this problem 3, the elements that belong in the set B is the number 2. 4 gives me a set name, so I'm going to write C and I'm going to write equals. And now I need to figure out what goes in C. You'll notice that in problems 1 and 2, the sets were given with word descriptions. I was able to use the word descriptions to create a roster form of the set. 3 and 4, the sets are given in set builder notation. And I'm able to use the set builder notation to figure out the elements of the set and then write them in roster form. 4 is a tricky question. I want natural numbers that are less than 1, and natural numbers, again, are 1, 2, 3, ... The elements of the set C in question 4 are natural numbers, but they're less than 1. These are my natural numbers. There's no natural number that's less than 1, so C is the empty set. There's no elements in C. So I could write that for an answer for number 4. C is the empty set. Or I can write C is the empty set. This is what's asked for because this is roster form. Roster form wants the set braces. But there are 2 ways to write a set with no elements. One is to write the empty braces, the set braces with nothing between them. The other is like a 0 with a line through it. 5 is kind of given in set builder notation. It doesn't have the vertical line, so it's not perfectly set builder notation. It tells me that the set name is D. And it also tells me that D contains natural numbers that are between 2 and 9. When I have a letter between 2 numbers with less than signs, then this is the same as M is a natural number. That's the comma. Or that's before the comma. The comma is the word and then a sentence for this is M is between 2 and 9, meaning it doesn't include the endpoints. And the numbers that are going to be in it are 3, 4, 5, 6, 7, and 8. I didn't need to use any ... dots because there are only 6 elements to write down. So in theory now, you should be able to do problems 25 through 34 on the text. And specifically, I assigned 27, 29, 31, and 33. So I'm going to get to the text just to take a peek at that style of problem and see what you can do. So let me just do 28 maybe. So in this section of problems, the instructions hopefully are the same as my instructions. Basically, I want to write each set in roster form. So let me just take, oh gosh, I can't do 26. I probably wouldn't have signed 25, but I probably could do 25. 26 wants me to list all the states in the U.S. whose names begin with I, like Iowa, Indiana, Illinois, Idaho. I'd probably forget one, so I won't do that one. Let me do 28, because 28 is an algebra one. 28 says I'm going to write C in roster form. So I'm going to write the letter C in equals, and inside I'm going to write all the answers to this equation. The equation was x plus 6 equals to 10. To solve this equation, I'm just going to minus 6 from both sides. The answer I'm going to get is 4. The only element in set C is the number 4. So the answer to 28 is going to be, in roster form, C is the set that contains the number 4. The rest of the problems, hopefully from my lecture, the problems that I did, you'll be able to do. Guaranteed, I would never give a problem like 25 or 26 on a test. I doubt that I'd even assign them for homework because not everyone would readily know the oceans in the world. I don't want you to go to the internet to have to find those. So each of the problems that I assigned between 25 and 34, you should be able to do without having to get outside resources. So try to do the odd problems. Check your answers in the back of the book, because for every odd answer problem that I assign, there's an answer in the book that you can check. And once you get done with that, then you can come back to the video. When you come back to the video, I'm going to be using set builder notation. And there are multiple ways when we get to this next group of problems to write correct answers. And maybe I'll do 2 for each. Maybe I won't, but maybe I will. So assuming you've paused the video, worked the problems, and now you're ready to go to the next group of problems, the next 3 problems that I have are supposed to help me with problems 43 through 50 in the section. your homework problems that are going to come from these 43 through 50 are these problems, 43 through 49. I don't know, I must do these in an opposite order. But after watching these problems, you should be able to do 43, 45, 47, and 49. Ask me to write a set in set builder notation. So when I do problem 1, set builder notation, by it's just the way it's constructed, I write the name of the set with an equal sign, then I write the set braces, and I write a vertical line. To the left of the vertical line, I usually pick a letter, and it doesn't matter which letter I pick, but X is such a nice letter, I'm going to pick X. And when I look at this list, the numbers 2, 3, and 4, they're all natural numbers. So I'm going to do this. I'm going to say X is a natural number. And then but it's not any natural number, and X is greater than 1, or X is greater than or equal to 2. So it's any natural number that's bigger than 1. That would be a perfect way to describe set D, but not the only way. There's probably 1,000 different ways to do it correctly, and X isn't even the letter you need to use. Another way to do this is say set D is a set of all X such that, and instead of writing the words X is a natural number, you can write the symbol X with an element sign and N. That means X is a natural number. Instead of the word and, I can put a comma. And then saying X is greater than 1 would be perfectly fine to write after the comma. I also could say something like this: X is greater than or equal to 2. And that, for me, would still have the numbers 2, 3, 4, 5, 6, 7, and go on forever. So both of these tell our set builder notation, and they tell me that D has the numbers 2, 3, 4, blah, blah, blah. Part 2 wants me to take A and write it in set builder notation. So I'm going to write A and then equals, and because we can do a variety of values, I'm going to say it's a set of all X such that, and now there's going to be, again, multiple things I can write to the right of this vertical bar that would tell me the numbers 1 through 5 are in the set. This would be a way to do it. I can say X is a natural number, because all those numbers are natural numbers. And then I can say and X is less than 6. If I look at the that would describe the numbers 1, 2, 3, 4, and 5 to me, because it's any natural number less than 6, and that's what that set is. Not the only way to do it. I can do something like this. I can say A equals, I don't even need to use a set of X. I can say N for number. A is a set of all N such that you can't really get away from this N isn't a natural number. If you don't put the N as a natural number part, then you allow fractions and decimals. So N is a natural number, and I'll use a comma for and. And another way to show that you're taking the numbers between 1 and 5 inclusive, I can say I can put N between the numbers 1 and 5. And when I put N between numbers, I only ever put less thans. Putting a greater than for one of those would be odd. And because I want N to include the endpoints, with the less than signs, I put or equal to. So this would be another acceptable way to say that describes that A is the set 1, 2, 3, 4, and 5. Both of them, what they have in common is they say that I'm dealing with a natural number. This probably is easier, saying that it's a natural number less than 6. This is a number between 1 and 5, including 1 and 5. Again, and there's probably other ways to write the set A down that are equivalently correct. If I go to 3, doing my set builder notation, I'm going to use the letter X. So it's a set of all X such that X is an even natural number. Oh gosh. There's multiple ways to do this. I'm not going to try to get as fancy as I might get, but I'm going to do this. I'm going to say X is an element of n, meaning x is a natural number, a comma, and, how about, oh gosh, how do I do this so I don't look foolish without, have some debates here, because I know how they would do this in higher level math, but I don't want to make this like a higher level math. So how about this? X, this is not that good, equals 2, 4, 6, 8, dot, dot, dot. This is not really an answer that a mathematician would write, but a mathematician would write an answer that you wouldn't probably care to look at right now. So this would be acceptable because it's technically fits the definition. It's in set builder form. It has the set brackets with a vertical line, and to the right of that vertical line is something that helps me describe the set. It probably would have been fine if I would have just said this: E equals the set of all x such that x equals 2, 4, 6, dot, dot, dot. Because I physically listed the elements of x, and those are natural numbers, I probably didn't need that part, because I could still, from both of these, determine that the numbers in the set are 2, 4, 6, 8, blah, 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 and so forth. So the idea now you should be able to do 43 through 50 in the section. So and 43 through 50 are on the top of page 48. If I look at a problem like 44 wants me to do the set A in set builder notation. So I'm going to write an A and an equals and make my set brackets. To the left, I'm going to use the letter X. And I'm going to say X is a natural number and X is. So we'll go X is an element of n because each of those are natural numbers, comma for the and. I like saying X is just less than 8. But you can write x between 1 and 7 with less than or equal to signs. But for me, saying x is less than 8 gives me the numbers 1 through 7. This is not the only answer for problem 44. It's an answer that fits what we want. It's in set builder notation, and from what I've written to the right of the vertical line, I can figure out that A has the numbers 1, 2, 3, 4, 5, 6, 7. There are definitely other ways to do that. So hopefully you paused the video and you did problems 43 through 50. And now you're ready to watch the next part of the video. Oh gosh. So I didn't do anything like problems 35 through 41. Go ahead and skip those. I know those aren't going to be on the review. They won't be on the test, and I'll delete them from the syllabus in the future, so that this video doesn't get to be any longer than it's already getting to be. All right. The next problems ask me to write a word description, and they're like problems 51 through 58 in section 2.1. And I didn't even ask you to do those for homework, which means they're not going to be on the test, but I'll do these anyways just so you see these. I didn't pick homework problems for these. And on top of not picking homework problems, I don't know what else to say. I'm going to write word descriptions for each of these and just get going. So I'm going to say D, and then I need to write something so that I know it's the numbers 2, 3, and 4. And these are all natural numbers, so I'm going to say it's going to be the set of natural numbers, because 2, 3, and 4 are natural numbers. And then after this, I can say greater than 1, and that would count the numbers 2, 3, and 4. Another way to do that, I could say greater than, so this would be options. I can say it's a set of natural numbers that says or, believe it or not, greater than 1. Or I can say it's a set of natural numbers greater than or equal to 2. Both of those would, for me, describe the infinite set that goes from 2 and forever. And then if I was doing something like 2, I can say A is the set of natural numbers, because those are all natural numbers. I can say less than 6, which would be nice. Or I could do something, and there's many ways to do this. Or I can say it's a set of natural numbers between 1 and 5. And if I put the word inclusive with the word between, then it includes the endpoints. So that would also be another way of saying it's the numbers 1, 2, 3, 4, and 5. It's the numbers between 1 and 5, but including 1 and 5 that are natural numbers. And then D, 3, D is the 1, 2, 3, 4. There's the 7 dwarfs. If I do this, spell that right. And that would be word descriptions that from the description I should be able to figure out what the set is. At 3 you might need the internet to figure that out. So we don't have to do any problems between 51 and 58 in the text, so I won't have you look at the text. This little section, these last couple pages, is supposed to prepare me for problems first 75 through 79, and then the first 75 through 78, then 79 through 84. So two sets are equal if they have exactly the same elements. So this set right here, this set that has the elements A, B, and C, it equals this set that has the set B, A, and C, equals because they have exactly the same elements. But these two sets, the set that has A, B, and C, does not equal the set that has 1, 2, and 3. They have the same number of elements. They both have 3 elements, but they're not equal. To be equal, they have to have exactly the same elements. Cardinal number are the number of elements in a set. Like if I gave you a set B, if I said B is the set 1, 2, 3, and 4, then I could say N parentheses B are the number of elements in B. So the number of elements in B would be 4. So the cardinal number of a finite set is the number of elements in the set. If I said C is the set A, B, C, D, E, I could say N parentheses C, the number of elements in C is 5. This little example here says find the cardinal number. That's the number of elements in A. So this problem gives me the set written in set builder notation, asks me to find the number or the elements in the set, and A is the natural numbers between 2 and 10. So A is going to have the numbers 3, 4, 5, 6, 7, 8, and 9, and the number of elements in A is going to be 7. So this little section here, the cardinal number of a set, is the number of elements in a set. And these problems, 75 and 77 on the syllabus, ask me to find cardinal numbers. So if I go to the text, problems 75, 76, 77, 78, and page 49, give me a list of sets and ask me to find the cardinal number. So if I was doing 76, 76 says find the number of elements in set B. B has 1, 2, 3, 4, 5, 6 elements in it. So I'd say N of B is 6. When you get to 77, the answer to 77 is going to be how many elements are in set C. Set C is the empty set. The empty set has 0 elements in it. So hopefully you're able to do the other problem in that section that I assigned but skipped. And then the last little bit of what I have written will help us do problems 79, 81, and 83. When I look at there's not much left in my handout here. The last thing I see is equivalence and two sets are equivalent if they have the same number of elements. So these sets that I wrote up top, the first two sets are equal because they have the exact same elements. They're also equivalent. To be equivalent, you can be equal, but you don't have to be equal. To be equivalent, you just have to have the same number of elements. So this set, the sets ABC and BAC are equal and equivalent. The set ABC and 1, 2, 3, they're not equal because they don't have exactly the same elements, but they're still equivalent. Because to be equivalent, you just have to have the same number of elements. And because each of these sets, the set ABC and the set 1, 2, and 3, both have 3 elements, that makes them equivalent sets. So these problems, oh gosh, let me just do them. Hopefully you can do these really quickly. I didn't realize this was here. This question says find the number of elements in A. It tells me what A is. The answer to number 1, the number of elements in that set is going to be 3. This question 2 says find the number of elements of B, where B is this set that has the letters A, C, E, O, and V. And hopefully you're able to quickly say the answer to that question, because N of B means find the number of elements in the set B, and the N of B here is going to be 5. These last 3 problems are using the words equivalent or equal, both and neither. So if I look at the sets described in this problem 1, they're equal because they both have exactly the same letters. They're equivalent because they both have 3. So these are both equivalent and equal. So I'm going to write both for what these are. Question 2 gives me 2 sets. They're not equal because they don't have exactly the same elements, but they are equivalent because they both have 5 elements. So for this set, I'm going to say that these are equivalent. And the last 2 sets, A and B, they're not equal because they don't have exactly the same elements. They're not equivalent because A has 3 elements and B has 4 elements. To be equivalent, they have to have the same number of elements. So for 3, I'm going to say these are neither equal nor they are equivalent. So now we should be able to do problems 79, 81, and 83. And let me just do problem 80 real quickly so you can just see where I'm getting at. So these problems, 79 through 84 in section 2.1, give me the same instructions. Are these sets equal, equivalent? Both are neither. If I look at problem 80, those 2 sets, A and B, aren't equal because they don't have exactly the same elements, but they are equivalent. They're equivalent because they both have 3 elements. So I'm not going to write both because they're not equal, but they are equivalent. So that's the end of section 2.1. There didn't happen to be anything in the notes that wasn't in this section. So hopefully you have the section, the homework done, and you're just kind of done with this section. If you wanted to, go back to my webpage and print out the review for chapter 2. If you open up the review, the first few problems on the review are probably problems that are for the kinds of problems we did in section 2.1. Before every test, we'll have a day that I don't do new material, that I do the review. But if you open that page up and you can identify the problems that come from section 2.1, and you can do those problems, and you'll be ready for the test questions that come out of this section. All right, well, thanks for watching.